Welcome, everyone. We have a highly unusual piece of source material on the table for today's deep dive.
We really do.
Normally, when we look into things like aerospace engineering or orbital mechanics, we are parsing through dense technical manuals.
Or white papers or sprawling historical biographies.
Right, exactly. But today, we are looking at something incredibly distilled. It is a 10-point transcript from a short video. I think it's essentially titled 10 Lines on Rocket in English, or The Rocket SO.
Yeah.
And it is exactly what it sounds like. It's 10 simple sentences that attempt to capture the entire mechanical and historical foundation of rocket science.
Which, is a fascinating exercise in reduction.
It really is.
Because when you strip away the complex aerospace jargon and the intimidating thermodynamics and the thousands of pages of schematics, you are forced to articulate the absolute core truths of a technology.
You have to find the essence.
Exactly. The author of this text had to decide what makes a rocket at its most fundamental level.
So, our mission today is to take these 10 unassuming lines and reverse engineer them. We are going to unpack the mechanics they describe, the history they touch upon, and the immense power required to make these simple statements a reality in the physical world.
I'm ready.
Okay, let's unpack this.
The best place to start is probably with the text's primary definition.
Right.
It immediately frames the rocket as a powerful and effective invention of science, designed to produce the force needed to move an object forward.
And the text makes it sound so straightforward,
Yeah.
A device to produce forward force. But that simplicity is highly deceptive, isn't it?
Oh, totally.
Because the challenge isn't just producing force, it's producing a sustained, directed force capable of overcoming the gravitational pull of an entire planet.
Precisely. And the source outlines exactly how that is achieved. It notes that rockets carry fuel that is burnt inside a chamber.
A chamber.
Yes. That single word chamber is doing an enormous amount of heavy lifting in this essay. Well, think about it. If you ignite highly volatile fuel in an open space, you just get a catastrophic release of thermal energy.
Just get a bomb.
Exactly, you get a bomb.
Yeah.
The invention of science the text refers to isn't actually the fuel itself, it's the containment vessel. By restricting that violent chemical reaction inside a meticulously engineered chamber, you are taking chaotic energy and forcing it to abide by strict physical boundaries.
So it operates under a similar mechanical paradigm to, say, an internal combustion engine cylinder.
Right.
But operating at the absolute razor's edge of metallurgical limits, you are dealing with temperatures and pressures that actively want to tear the vehicle apart.
It's actively trying to explode in every direction.
Yeah. And the text neatly divides the approach to this propulsion problem into two camps. It notes that rocket fuel can be either liquid or solid.
A very important distinction.
It really is a great reminder of how we've engineered two completely different mechanical paradigms to solve the exact same problem.
It's a crucial distinction because solid fuel and liquid fuel represent two entirely different philosophies of aerospace engineering.
Break that down a bit for us.
Sure. Solid fuel is essentially a highly controlled, continuous explosive. The fuel and the oxidizer are mixed together into a dense propellant. And once you ignite a solid rocket booster, you cannot turn it off.
It's just going.
It is fully committed to burning until the chemical reaction has exhausted every single ounce of material. It offers incredible thrust and reliability, but zero operational flexibility.
Which contrasts sharply with liquid fuel systems, because a liquid fuel system requires a staggering amount of auxiliary engineering. You aren't just lighting a solid block on fire, you are dealing with cryogenic temperatures, complex plumbing, and turbopumps.
Oh, the turbopumps?
Right. Turbopumps that have to force massive volumes of liquid fuel and liquid oxidizer into the combustion chamber at the exact right ratio, at the exact right pressure.
And the complexity of a liquid fuel engine is just mind-blowing. The turbopumps alone often generate tens of thousands of horsepower just to feed the main combustion cycle.
Just to move the liquid.
Exactly. But the trade-off for all that immense mechanical complexity is control. You can throttle a liquid engine, you can shut it down, and in some cases you can even restart it.
And the fact that the text places these two vastly different engineering marvels side by side really highlights the versatility required to achieve orbit.
It does.
And what both of these fuel systems ultimately do brings us to the next line in the source material. It states, quote, "When the fuel burns, it gives off gas that pushes the rocket forward."
Yeah.
Again, the text strips a monumental physics problem down to a single sentence. You burn fuel, gas expands, the object gets pushed.
What's fascinating here is how this rudimentary release of gas is the sole driving force behind everything we have ever sent into the cosmos.
Sole driving force.
Yes, it is the purest expression of Newtonian mechanics,
Yeah.
specifically the third law of motion. Every action has an equal and opposite reaction. The chemical reaction in the chamber creates rapidly expanding high-pressure gas. The chamber then directs that gas out of a nozzle at the rear of the vehicle.
It funnels it.
Right. And because that gas is being expelled backwards with such violent velocity and mass, the physical body of the rocket has absolutely no choice but to be pushed in the exact opposite direction.
It is thrust generated through mass expulsion. You are literally throwing mass out the back of the vehicle as fast as chemically possible to force the rest of the vehicle forward.
That is exactly what is happening.
But the engineering required to survive that process is one thing. The destination is another thing entirely.
Right.
Because the text shifts from the mechanics of the push to the ultimate goal. It states quite simply that rockets are generally used to launch spacecrafts to space.
Which introduces an entirely new set of physical constraints. Pushing an object forward on the ground or through the lower atmosphere is relatively trivial. But pushing an object upward, fighting a constant deceleration vector of 9.8 meters per second squared from Earth's gravity while carrying a payload, that requires a monumental scaling of the mechanics we just discussed.
And the source material doesn't shy away from the sheer math of that challenge. It provides a very specific, staggering metric. The text states that a rocket must travel at a speed of at least 7.9 kilometers per second to reach space.
Yes.
Here's where it gets really interesting. Because 7.9 kilometers per second isn't just a random large number. It is a highly specific threshold.
That number is orbital velocity for low Earth orbit. It is the fundamental speed limit of our planet's gravitational well.
Explain how that works.
Well, if you go slower than that, you might reach space momentarily on a suborbital trajectory, but gravity will just pull you right back down to the surface.
You just fall back down.
Exactly. To actually stay in space, to orbit, you have to be moving sideways so incredibly fast that as gravity pulls you down, the curvature of the Earth falls away beneath you at the exact same rate.
That's wild to think about.
You are essentially in a state of continuous freefall, constantly missing the ground. And the speed required to achieve that delicate balancing act is 7.9 kilometers per second.
To put that in perspective for you listening, 7.9 kilometers a second is roughly Mach 23.
Mach 23.
You are crossing the equivalent of a major metropolitan city in the time it takes to blink.
It's incomprehensible.
The sheer aerodynamic violence of pushing a physical object through the Earth's atmosphere at that speed is difficult to overstate.
The atmosphere practically becomes a physical wall at those speeds.
Yeah.
The friction and dynamic pressure, which is often referred to as max Q during a launch, exerts immense structural stress on the vehicle. The air in front of the rocket is being compressed so rapidly that it heats up to thousands of degrees.
So the vehicle isn't just fighting gravity.
No, it is fighting the very air around it, all while essentially riding a controlled detonation.
And connecting this back to the fuel paradigms we discussed earlier, reaching 7.9 kilometers per second exposes the brutal reality of the rocket equation.
The tyranny of the rocket equation.
Exactly. To go that fast, you need a massive amount of fuel. But fuel is heavy, so to lift that heavy fuel, you need even more fuel.
Which adds more weight.
Which adds more weight.
It is a vicious cycle of diminishing returns. The vast majority of a rocket's mass, often upwards of 85 to 90%, is just propellant.
Wow.
You are building an enormous flying fuel tank just to get a tiny percentage of the overall mass, the actual spacecraft, up to that critical 7.9 kilometers per second threshold. The efficiency of that combustion chamber has to be near absolute perfection because every gram of wasted energy is payload that doesn't make it to orbit.
Which makes the historical detour in our source text so compelling. The essay takes a sudden step back from orbital velocity in modern spacecraft to point out that early rockets were made by filling bamboo cases with gunpowder.
Right.
It's a brilliant historical anchor that forces us to look at the origins of this technology.
It is a stark juxtaposition, but mechanically speaking, the bamboo and gunpowder serve the exact same function as the modern solid rocket booster.
Really, bamboo?
Yes. Bamboo is essentially nature's composite material. It is a hollow, fibrous tube with immense tensile strength relative to its weight. It acts as the primitive combustion chamber.
And the gunpowder.
Gunpowder, which is a mixture of sulfur, charcoal, and potassium nitrate, acts as the primitive solid fuel.
So you pack the volatile chemical mixture into the natural containment vessel, ignite it, and let the expanding gas push it forward.
Exactly.
The physics haven't changed a single degree over the centuries, only the materials have.
Only the materials and the math.
Right. And the text bridges this massive technological gap by mentioning the evolution toward the father of modern rockets.
That phrasing is critical.
Tell me why.
Whether the text implies Robert Goddard, Konstantin Tsiolkovsky, or Hermann Oberth, the reference to a father of modern rockets signifies a profound paradigm shift.
Okay.
For centuries, rockets were an empirical technology. Artisans built them through trial and error, adjusting gunpowder ratios by feel. The birth of modern rocketry marked the moment humanity transitioned from alchemy to rigorous mathematical analysis.
We started doing the math.
Yes, it was the moment we began calculating exhaust velocities, mass fractions, and orbital trajectories before bending a single piece of metal.
So we went from stuffing powder into a piece of wood to meticulously calculating the thermodynamic efficiency of liquid hydrogen and liquid oxygen.
That's the leap.
But the text makes a point to show that as the science matured, the applications of the technology splintered in vastly different directions. The source lists the primary uses for this powerful invention. It says they are used for launching spacecrafts, shooting missiles, and fireworks.
If we connect this to the bigger picture, this short list presents a profound philosophical commentary on the nature of technological advancement.
How so?
The rocket itself is entirely agnostic. The combustion chamber, the expanding gas, the Newtonian physics, these elements possess no inherent morality.
There's just physics.
Right. The intent of the technology is entirely dictated by the payload we choose to place at the top of the vehicle.
It really is the ultimate spectrum of human behavior represented by a single mechanical principle. I mean, look, fireworks.
Yeah, fireworks.
We use this powerful invention of science for pure aesthetic celebration. We engineer precise chemical reactions to paint the night sky with color, utilizing the physics of thrust simply to entertain our communities and mark cultural milestones.
And sitting on the exact opposite end of that moral spectrum are missiles.
Right.
The exact same aerodynamic principles, the exact same reliance on solid or liquid fuels to achieve rapid velocity, but engineered to deliver destructive payloads. It is the weaponization of the Newtonian push, turning the capability to cross vast distances quickly into a mechanism for conflict.
And then positioned above both of those is the pursuit of exploration. Launching spacecrafts.
Yes.
Using this technology to push satellites into orbit that monitor our climate, or sending probes to the outer edges of the solar system, or carrying human beings beyond the confines of our atmosphere.
It is a stark triad: celebration, annihilation, and exploration. The text casually lists these three applications side by side, but they represent the deepest contradictions of human ingenuity. The same mathematical formulas that allow a warhead to strike a target on the other side of the globe are the exact same formulas used to safely land a rover on the surface of Mars.
What stands out to you, listening right now, when you consider that spectrum? It is rare to find a single invention that touches the absolute extremes of joy, destruction, and scientific nobility.
Very rare.
The rocket is a mirror reflecting our own societal choices. The fire inside the chamber just pushes. We're the ones who decide where it is pointing and what it is carrying.
It highlights the immense responsibility that comes with mastering the physical laws of our universe.
It really does.
The transition from bamboo cases to orbital launch vehicles didn't just give us new capabilities, it amplified our existing nature. The power to break the bonds of Earth's gravity is inextricably linked to the power to inflict unprecedented harm or to inspire unprecedented wonder.
Let's take a moment to recap the journey this 10-line essay has taken us on today. We started with the foundational definition of the rocket as an engine of progress, utilizing the simple but devastatingly powerful mechanic of burning solid or liquid fuel inside a carefully engineered chamber.
And we explored how that containment of chaotic energy allows expanding gas to generate the thrust necessary to overcome inertia and gravity.
Right. We then analyzed the staggering physical requirements of achieving spaceflight, specifically the need to reach an orbital velocity of at least 7.9 kilometers per second.
A speed that turns the atmosphere into a physical barrier and demands absolute mechanical perfection.
Finally, we traced the historical and philosophical arc of the technology. We looked at the primitive ingenuity of packing gunpowder into bamboo, the mathematical revolution brought about by the founders of modern aerospace engineering, and the stark agnostic duality of an invention used equally for fireworks, missiles, and spacecrafts.
It is a comprehensive overview of aerospace dynamics, distilled into a handful of sentences.
So, what does this all mean? When we look at these foundational truths laid out together, what is the core synthesis we should take away from this exercise?
I think the most crucial takeaway is recognizing how mastering this one specific mechanical paradigm fundamentally altered our relationship with the cosmos.
Tell me more about that.
Well, for the vast majority of human history, we were entirely bound to a two-dimensional surface. We could observe the universe, but we were isolated from it by the invisible wall of our planet's gravity.
We were stuck here.
We were stuck. But by learning to meticulously control a continuous explosion inside a metal chamber, we discovered the key to the lock. The rocket proved that our physical isolation was not absolute.
That's a beautiful way to put it.
It demonstrated that with enough intellectual rigor, material science, and applied physics, even the immense gravitational pull of a planet can be overcome. It transformed the sky from an impenetrable ceiling into a navigable ocean.
The sky is no longer a ceiling, it is an ocean. That framing perfectly captures the scale of the achievement. And as we conclude our analysis today, I want to leave you, our listener, with a final thought to explore on your own.
Okay.
We spent time today looking back at the origins of this technology. The simple, almost crude concept of filling a hollow piece of bamboo with chemical powder. At the time, that was just a curiosity, a localized mechanism for celebration or simple warfare.
Right.
Yet the foundational physics inside that piece of bamboo contained the seeds of a technology that would eventually carry humans to the moon. So look at the world around you right now.
What do you see?
Exactly. If humanity was able to take bamboo and gunpowder and scale it up into a vehicle capable of traveling 7.9 kilometers per second to escape the Earth, what seemingly mundane, everyday technology sitting in our labs, our garages, or even on our desks right now is actually the primitive bamboo casing for our next monumental leap into the unknown.
It is an essential question. The foundational mechanics of the future rarely look like breakthroughs in their infancy. They look like simple, curious applications of basic principles waiting to be scaled.
Exactly. Thank you all so much for joining us on this deep dive. It is a privilege to take these seemingly simple texts and extract the vast technological and philosophical networks hidden beneath their surface with you. Keep questioning the mechanics of the world around you, keep looking for those hidden complexities, and we will see you next time. Goodbye.
Goodbye, everyone.